All right, guys, welcome to our lesson on what's called molarity. All right, here we go. Obviously, I pulled you over because you were texting and driving. No, I wasn't. I don't even know how to text. I'm still writing you a ticket. OMG. All right. So, you guys, here's a little question for you. You don't have to write it down. What do you think is the difference between an acid you can drink and one that might kill you, right? You guys, we take, you tend to consume acidic substances all the time. What's the biggest difference? Hopefully you guys would realize that oftentimes the biggest difference is it's the concentration. Now, obviously, the type of acid will obviously affect it as well. There's what are called strong and weak acids, strong acids being more harmful than weak acids, but we'll talk about that when we get into our acid base unit. But right now, today, we're focusing on concentration. The concentration of a solution is measured in, and you might guess it, in molarity. That's what molarity is. It's a measure of concentration. And you guys will see, as you might expect, molarity sounds like moles, which we were somewhat familiar with, and that's where we get the concentration unit from. It comes from moles. And a concentration, you guys should know, is an amount within a given space. So we have an amount, which is moles, within a given space. Liters is our typical unit that we use for volume or space. So that would be a measure of concentration. How many moles of a substance do we have within a liter of solution? So once again, when we talk about molarity, we're talking about typically aqueous solutions, things dissolved in water, all right? Tags, what we'll use is, right, you guys remember we can abbreviate moles with MOL, okay? So we save an E. Liters is abbreviated with a big L. Then we can further abbreviate this, moles per liter. Molarity is abbreviated with a big M. When you see a big M, you're like, that is molar. So here would be a properly labeled solution. Like I have solutions in my back area, and sometimes lab techs haven't labeled it properly, and they'll have a container that might say NaCl on it. You know, if it's NaCl, I know how to, right? You guys would know nomenclature, like, oh, that's a sodium chloride solution. But you would think, guys, what else would be important to know about that solution besides its identity, the fact that it's salt solution? You'd also want to know its what? Its concentration. So not only would you have identify what it is, you would indicate the concentration of that solution. So this is how it would be read if it was labeled like such. 6 molar, sounds kind of weird, but it's called 6 molar NaCl solution. What does that tell me? I know I have salt dissolved in the water, and how much salt do I have? 6 moles. For every liter of solution, I have 6 moles of salt dissolved. Okay, you guys, we're going to do several problems here, so hopefully you guys write down the problem, and then we're going to work it out. So if we have 0.3 moles of NaCl, and we dissolve it in a volume of 500 milliliters, what's the molarity? So let's say we have that condition. You guys, if it asks you what the molarity is, it's really easy. You just use the molarity equation. Molarity is moles over liter. So I'm looking for molarity, and once again, I'll just write big M. Now it's just a matter of punching things in. On the top goes the moles. How many moles of my solute? This is a solute. That's the substance that dissolves, which is the salt. I have 0.3 moles. And I'm dividing that. It's per, now you guys think about what do we have to do? It says per liter, but we are given the volume in milliliters, 500 milliliters. 500 milliliters is actually half a liter. A liter is 1,000 milliliters. So 500 milliliters, what I'd want to do is I'd want to convert it into liters. So once again, 500 milliliters, if 1 liter is 1,000 milliliters, you should know 500 milliliters is half a liter. Another way you could look at it is if there's 1,000 milliliters in a liter, there's 3 zeros in 1,000. That means I would divide by 1,000, which means I would move the decimal over 3 places because it differs by 3 factors of 10. 1, 2, 3. 500 milliliters is the same thing as 0.5 liters. So that's what I would put in here, 0.5 liters. So then I do 0.3 divided by 0.5, and what do I get? I get 0.6, and I could write moles per liter. The easier thing to do is to write big M molar. So what would I write on this solution if I was making a solution to store it where somebody else would come by and know not only what it is, but the concentration? I'd write 0.6 molar NaCl. Okay. Here's another one. So let's say we have 120 grams of NaOH. NaOH is sodium hydroxide. You guys, that's kind of like an oven clean. It's like the stuff that makes oven cleaner really, really nasty stuff. It's a really, what's called a strong base when you see this OH group combined with the metal, but nonetheless. 120 grams of NaOH are dissolved to volume of 2 liter. What's the molarity? Okay, so now, once again, we still have we're asked for the molarity, so it's still this equation, okay? But now, hopefully you guys will notice something. What do you guys notice if you're looking at the information that's given? We are given the solute. That's what is dissolved in the water. But what are we given about the solute? We're given the grams. What do you guys think we're going to have to do? Aren't we going to have to convert to moles, right? So we should know how to do that, guys. 120 grams of NaOH. Remember, we set up a unit analysis. I want to convert it to moles of NaOH. So how do I do that? You guys, the link between grams and moles is always the molar mass, otherwise known as the molecular weight, where you find in the periodic table. So if you look at the periodic table, sodium weighs 23, oxygen weighs 16, and hydrogen weighs 1. You add those together, it's 40 grams per mole. So now I can use this information in here. I just need to know which one goes on top and which one goes on bottom. Notice I'm starting at grams on top. So I'm going to put the grams on the bottom. 40 grams of NaOH is equivalent to 1 mole of NaOH. So you'll notice grams cancels, and I see I have a number on top and a number on bottom. I'm going to divide 120 divided by 40 is 3 moles of NaOH. That's how much NaOH I have. So I'm going to put that on top. See how we just figured out the moles? And what I'm going to divide it by? The volume of my whole solution. And the solution is, I have a 2 liter solution. So 3 moles divided by 2, 3 divided by 2 is 1.5. Once again, moles per liter, I'm going to call it molar. This is a 1.5 molar NaOH solution. Picks up some mail. He said, "What's that?" He said, "It's from my mom. She wanted me to know that she sent me an email." So she sent him a snail mail letter saying, "Honey, I just typed you an email." You guys, you know, I would normally say for time's sake, but you guys can pause and go as fast as you want anyways, but I just said you wouldn't even have to write it down just to kind of move along here. Now this is different, guys. Now you'll notice, look, it says, "In what volume must 1 mole of," this is silver nitrate, "be dissolved?" So this, usually when you're talking about dissolved, usually it'll be a solid, right, dissolved in water, "to make a 0.5 molar silver nitrate solution." Okay, so this time, notice, look what it's asking us to find. It's not asking us to find the molarity, it's asking us to find the volume. So if we're not looking for the molarity, we're going to have to rearrange this equation to isolate what it is we're looking for. It says in what volume. So what here are we looking for? You guys should know liter is a volume unit. So if I want to solve for this, the volume component, I got to first of all get it out of the bottom and then also get it by itself. First of all, how do we get it out of the bottom? You multiply both sides by that. Right? You always do the inverse operation. If I'm dividing by something to get rid of it, you do the inverse operation. In this case is multiply. Look, liter on top, liter on bottom cancel. So now look, now liters is out of the bottom, but now I just need to get it by itself. What do I got to do? I got to divide by molarity. That's how I get rid of the molarity. So now I have the liters, the volume of liters is the moles over the molarity. So now let's see if we got the information. We know we have 1 mole of our silver nitrate. Oh, so that's my solute. So I got 1 mole. Divided by the concentration. The concentration is 0.5 molar. So notice if I put 0.5, if I put a big M here, there's nothing to cancel out. When you put molar, remember what molar means? It means moles per liter. So I think it's preferable to write it what it actually means, because then you can see, check this out, look, mole divided by mole cancels out. Liter on the bottom of the bottom ultimately goes on top. So what do? I just now have to, and you'll see the only unit I have left is liters, which is what I wanted. So I'm going to go 1 divided by half. If you take 1 divided by half, just put that in your calculator, 1 divided by 0.5 or half, you're going to get 2. And my unit was 2 liters. So what did I just figure out? If I want to make this solution with this much silver nitrate, I would take 1 mole of silver nitrate, which we could talk about how much that is, and I would dissolve it in a solution to the point at which I had 2 liters of that solution. By the way, let me bring it up. I want to show you guys how you would actually make the solution. So you guys, here's how you make a solution. You first have a volumetric flask. That would look something like this. Okay, it's a flask with a very long neck. It's going to allow you to measure volumes more precisely because where you're measuring it to, that place is very narrow. So you guys remember we talked about the meniscus. The meniscus would be very small, and therefore the possibility of error would be minimal. So typical solution is a solid dissolved in water. Here's how you would do it. You'd first, if you're making your solution, you'd first have to figure out how much solute you need. Let's just say it's a salt solution, okay? So then I would put however much salt I needed, and that's where we use calculations like this, and we'll look at one here in just shortly to figure out how we determine that. So then I put my solid in my flask. Then let's say, and I would use the appropriate volumetric flask. Let's say I was making 100 milliliters of that solution. Well, then I would use a 100 milliliter volumetric flask, and what you'll see, there's a line on these volumetric flasks. That tells you if you filled it to that line, that's where you have 100 milliliters. So you put your solid in. Then what you'll notice is you take your water. Obviously, you're going to dissolve it. You're going to add water, but notice it's not just a one-step process. What you're going to do is you're going to add water, and then at this point, you notice what we haven't filled it up to the designated volume yet. You're going to put the water in. Then what do you guys think you're going to do? Then you're going to swirl it. You guys, what's the whole purpose of swirling it? When you guys agree, don't you need to dissolve the solid in the water? You want to dissolve it. And then once it's fully dissolved, you would proceed to add more water until you've reached the designated volume. Somebody might ask, why do you have to do it 2 steps? Why can't you just put the solid in and then just put the water in up to the mark and then dissolve it? Because what you'll find is, if you do that and you get a certain volume and then you dissolve it afterward, the volume can change. In fact, when that solute dissolves, oftentimes the volume will go a little bit lower, and so you'll end up with a volume that's not consistent with what you need. So you dissolve it first via swirling, and then you proceed to add enough water to get the necessary volume. Okay, guys, we're going to finish with one last problem here. So, you guys write this down. This is a good thing for your notes. How many grams of zinc chloride must be dissolved in 100 milliliters to make a 0.1 molar zinc chloride solution? You guys, this would be typical of what a professor would ask a lab tech to do. You guys remember we're kind of showing you guys how to make solutions here because that's a big component of what chemists do, lab techs in particular do. So let's say we needed to, for an experiment, we needed to make 100 milliliters of a 0.1 molar zinc chloride solution. Well, you're thinking, okay, zinc chloride solution. What would you guys do first? You guys know you would go to your stock room. I'd go in the back in the stock room, and then I'd find my zinc chloride. Now this is like super old, like 1960s or something like that. But anyways, because I've never really needed to use zinc chloride. So I would get my zinc chloride because I know I'm going to need this for my solution. I need to make 100 milliliters of a 0.1 molar solution. You guys, I would ask you now, what would be your question at this point? You're going to get your zinc chloride. What do I want to know about this zinc chloride right now? Wouldn't you guys agree? Don't I want to know how much of this zinc chloride, this solid, do I need in order to make 100 milliliters of a 0.1 molar solution? So what are we going to have to do? We're going to have to do a calculation to kind of figure that out. So, and you guys think about it, what do you think, what would be a unit I would want to know the amount of that? You think if I knew the amount of moles, if I knew the amount of moles, that probably wouldn't help me too much because how much would a certain amount of moles be? But if I could figure out the what that I need, the gram weight, then once I get that, then I could put that on a gram scale, right? You guys know an electronic balance, weigh out that certain amount of zinc chloride I need, and then use that to make my solution. So what we might want to do then is figure out how much zinc chloride, how many grams of zinc chloride do I need to make that solution? So this one's a little more difficult. You guys remember, we're always working with the molarity equation. And what you can do is, you know what you can do, even if you were lost and you didn't really know where you're going with it, you might think, oh, I want to try to get the amount of grams of zinc chloride. Remember we were saying that? Maybe because we're kind of thinking ahead, what information do I need to know in order to make this solution? Oh, you know, in fact, actually it tells you straight up how many grams of zinc chloride must be used. Another thing you could have done is, if you didn't really know where you were going with that, you just wanted to make the solution, you could just think, well, think about the information that you have, and then how could I use my equation to get information I don't have? Notice, what do I give you? I give you the milliliters, which ultimately tells you the volume, so I could get the liters, right? And I'm also given the molarity. So if I know the molarity of a solution, I know the volume of the solution, what could I figure out? You could figure out the moles. In fact, that's what we would do. So we're gonna try to solve for the moles. So if I want to solve for moles, I want to get it by itself. How do I get rid of liters? I do the inverse operation. If it's divide by liters, I'm going to multiply it by liters. What I do to one side, I do to the other, and that's what I got. And you guys, look at how this is ultimately going to help us. So I got my liters of solution. Once again, I know I have 100 milliliters of solution. Remember, it's 1,000 milliliters in a liter. Just helps to know some of those conversions. 100. Once again, what do you do to convert from milliliters to liters? You're going to just divide by 1,000. 3 zeros in 1,000. 3 factors of 10. I'm going to move the decimal over 3 places. So 100 milliliters is 1/10 of a liter, or 0.1 liters. So I have 0.1 liters times the molarity, which was 0.1 molar. And you remember when we're dealing with molar, I can just write it as moles per liter, because then you guys can see what happens. Liter on top, liter on bottom cancels. Now I'm going 0.1 times 0.1. What do I get? 0.01 moles of zinc chloride. What did I just figure out? This is how many moles of zinc chloride are in this solution right here. But once again, that's not really going to help me. So now I know I need 0.01 moles of zinc chloride. How much is that? You know, I got my spatula. Does anyone know how much 0.01 moles is? No. What could we figure out? The gram weight associated with that, because then I could use an electronic scale. So we've got one last step here, guys. 0.01 moles of zinc chloride. And then what do I want to do? I want to figure out how many grams of zinc chloride is that equivalent to. Once again, I'm going to go from moles to grams. You guys remember what the link is? It's the molar mass. So I'm going to look up the molar mass. And you know what? I remember chlorine. Chlorine is 35.5. So if there's 35.5, right, that's going to be 71. And then zinc, unfortunately, I haven't memorized. So you guys see, I'm reliant on my, I think it's 65 or something. I'm reliant, yeah, it's 65.4 grams per mole. So then I'm going to add, this is the weight of zinc, 65.4. So it's 136.4. Remember how to say it? Grams per mole. That's the link between grams and moles. So I'm going to use that right here. Look at this time I have moles on top. So this time I want to put the 1 mole on the bottom. 1 mole is equivalent to 136.4 grams. Moles cancel. 0.01 times 136.4. You guys see it's to the hundredths place. That's like 1/100th. So basically what that just tells me is I'm just going to move the decimal over, because you guys know if I take this really small number times this, won't this number become smaller? So I know I'm going to move the decimal to the left 2 places. If you didn't follow all that and that got confusing, just punch in your calculator 0.01 times 136.4. But either way, the decimal just moves over 2 places, and I'm going to get 1.364 grams of zinc chloride. So what did I just figure out, guys? That's about 1.4, but you know, it depends on what the precision you need. Technically, we're limited to 1 significant digit. So therefore, really, you know, but either way, if we had the precision to measure it, we could measure to 1.364. So basically, I need 1.364, or essentially about 1.4 grams of zinc chloride. So that's what I would do. I would put this, I would have a weigh tray, and I would proceed to take with my spatula, take out, and I would put on the weigh tray until that electronic scale read 1.364. Then I would take that zinc chloride, 1.364 grams of zinc chloride. You guys remember what we do? I would get a volumetric flask. How big a volumetric flask do I need? 100 milliliter one. I would put that zinc chloride, 1.364 grams of zinc chloride, into my volumetric flask. Then you guys remember what you do? You add a little bit of water. Then what will we do? A little swirl action to make sure it's dissolved. Once it's fully dissolved, I would proceed to add more water until I've reached that 100 milliliter mark on my volumetric flask. And then what do I have here? I have 100 milliliters of a 0.1 molar zinc chloride solution. You guys, that's primarily what lab techs do. And if you have that skill, that's what would cause a lab tech to be paid more than, you know, someone slinging burgers at Mickey D's. So, all right, you guys, that's all we got for today. Until next time.